Greetings to everyone. We are moving into the second part of the fourth unit, that is thick cylinders. Okay, so thin cylinder we have discussed in the last classes. So what is the difference between thin cylinder and the thick cylinder, that we are going to discuss first. Okay, the thing is, uh, the thickness of wall is less than 1/20th of internal diameter, then the cylinder is said to be thin cylinder. Okay, if the same, the thickness of wall is greater than 1/20th of internal diameter, then the cylinder is said to be thick cylinder. So this is with respect to dimension. So next, with respect to stresses. Okay, so thin cylinder have, and we are assuming that this is our wall thickness T. So the stresses developed in the circumferential, there is hoop stress. Okay, hoop stress will be uniform throughout the cross section. Okay, that is circumferential stress. Here, because of the thickness, the stress will be is not uniform. Okay, so internal side it is higher value and the external side it is lesser value. So like that we are assuming. Okay, so the circumferential stress will be not uniform due to the thickness of wall, due to the thickness of wall. So here, so maximum at the inner circumference, so the hoop stress is maximum in the inner surface or inner circumference of the cylinder, and minimum, okay, and minimum in the outer circumference of the cylinder. So this is the these are all the constraints we can have. Okay, so with respect to this, we can classify what is thin cylinder and what is thick cylinders. Okay, if we are asking for classification or differentiation. Okay, so with respect to thickness and with respect to stress, now let us move on to the formulas which we are going to use for the uh, thick cylinders. Okay, so stresses in a thick cylinder. So we are having some constraints. So I'm not going to derive the complete equation. Just I'm going to tell the formula for the thin thick cylinder. Okay. So the thick cylinder diagram will be like this. This is our longitudinal axis. So this is with respect to the longitudinal axis. Okay. And the inner dimension is R1 from the centroid, and the outer dimensions is R2. That is the radius for the inner circumference and the radius for the outer circumference. And the length is about L. So with respect to its cross section, so this is the cross section. Cross section of the thick cylinder. Okay. So if I'm going to consider a small strip, then it becomes like this. So this is the strip. Okay. So now with respect to the internal thing is R1, and with respect to outer dimension it is R2. Okay. And up to the strip the thickness is small t, sorry, dx. So up to this we are calling it as x, and the small strip is dx. Okay, this is with respect to our diagram. Now let us move on to the R2 is equal to external radius of the cylinder, and R1 is equal to internal radius of the cylinder. L equal to length of the cylinder. L equal to length of the cylinder, and Px is equal to, so I will draw another diagram. This is with respect to the strip. So Here we are going to take that as x. Okay, and here the stresses are acting. So these stresses are px. Okay, and in the outer cell it is px into x plus or px plus dpx. Thickness is px. Okay, so whereas px is equal to radial pressure on the inner surface of the ring. Radial pressure on the inner surface of the spring. Then px plus dpx is equal to radial pressure on the outer surface of the ring. Then sigma x is equal to hoop stress. Hoop stress induced in the ring. Induced in the ring. This is due to thickness. Okay. So these are all the things we can have. So now we can have the formula. So final formula I'm going to tell. So this is nothing but px is equal to b divided by x squared minus a. Similarly, sigma x is equal to b by x squared plus a. So these two are the equation. Okay. So internal pressure is equal to radial pressure is equal to px is equal to b by x squared minus a. Similarly, sigma x, that is hoop stress induced in the ring, sigma x is equal to b divided by x squared plus a. Okay. Uh, so whereas px is equal to radial compressive stress, radial compressive stress, and sigma x is nothing but a hoop stress. Okay, hoop stress or circumferential stress, hoop or circumferential stress. This is tensile stress. Okay, and sigma 2 is available. So this is nothing but our longitudinal stress. This is also tensile. Okay, now the above two equation, that is px and sigma x, the are called Lami's equation. Okay, the above px and sigma x equations are called Lami's equation. Okay, and a comma b are the constants obtained from the boundary conditions, obtained from the boundary conditions. Okay, so what are all the boundary conditions that we will discuss right now? So the boundary conditions are the boundary conditions are where first one at x is equal to r1. So with respect to this, okay, at x is equal to r1 means then it is a uh, fluid pressure inside the cylinder. Okay, so that px is equal to 0. Okay, p0. And if x is equal to r2, then the pressure it will be available here. Okay, now then it is nothing but atmospheric pressure. Okay, so that is the boundary condition. If at x is equal to r1, then px is equal to p0, or the pressure of fluid, either gas or liquid. Okay, now fluid inside the cylinder. And x is equal to r2, then px is equal to 0 at atmospheric pressure. At atmospheric pressure. So by using this condition, we can find out the value of A and B. Then if you are going to substitute those A and B value in Px and sigma x, then automatically we can find out the values of those hoop stresses and mm, pressure, that is radial pressure or radial stress. Okay, so after getting the values of A and B, we can calculate hoop stress, that is radial stress px and hoop stress sigma x. Okay, so this is the constraint. Now let us move on to the problem. Okay, problem 1 related to thick cylinder. Determine the maximum and minimum hoop stresses. Determine the maximum and minimum hoop stress across the section. Across the section of a pipe of 400 internal diameter. 400 internal diameter, comma 100 thick. So the thickness is 100 when the pipe contains when the pipe contains a fluid at a pressure of 8 Newton per mm square. Also sketch the radial pressure distribution. Also sketch the radial pressure distribution and hoop stress distribution across the section. Okay, now the given data are, so maximum and minimum hoop stress we have to find out. So the given data is the section of pipe 400 internal diameter. Okay, the internal internal dia, we can say that R1 is equal to 400 mm. Sorry, this is radius. So I'm saying D1, we can say D is equal to 400 mm, and therefore radius or internal radius R1 is equal to 400 divided by 2, such that the answer is 200 mm. Then they have given 100 mm thick. So the thickness of wall T is equal to 100 mm. Therefore, outer dia capital D is equal to small d plus 2 times of thickness. So it becomes 600 mm. Therefore, outer radius R2 is equal to 600 divided by 2, it becomes 300 mm. Okay. Then they have that when the pipe contains a fluid at a pressure of 8 Newton per mm square. So fluid pressure P naught is equal to 8 Newton per mm square. Then after, okay, find the maximum and minimum hoop stress. Find the minimum and maximum hoop stress. So first is solution part. So first of all, we know the formula, that is the radial pressure. Okay, radial pressure Px is equal to, okay, B by x squared minus A. B by x squared minus A. Similarly, hoop stress, there is the hoop stress. Sigma x is equal to B by x squared plus A. So these are the formula, that is from the Laplace equation. So here we know the boundary condition, that is boundary condition at x is equal to R1, then Px is equal to P0. Okay. So whereas P0 value we have know that that is internal fluid pressure. So fluid pressure is nothing but 8 Newton per mm square. Okay. So from this value we are going to calculate the thing. Okay. So second condition, we all know that at x is equal to R2, then Px is equal to 0. So these two conditions we know that. So from this we are going to calculate those values. So first boundary condition. So at x is equal to R1, that is 200 mm, then Px is equal to P naught. Okay, that is nothing but 8 Newton per mm square. So we have to write the equation, that is Px, P by x squared, instead of x squared. Okay, full formula we can write, minus A is equal to 8 Newton per mm square. So we have to substitute x is equal to R1. So B by R1, 200 squared minus A is equal to 8 Newton per mm square. So this is equation number 1. Next, second boundary condition. that is x is equal to R2, that is 300 mm, then our px value is equal to 0. So b by r squared, r2 squared, x2, that is 300 squared minus, sorry, plus minus a is equal to 0. This is equation number 2. So if I'm going to deduct 1 minus 2, then I can get the solution. Okay, so 1 minus 2 becomes, so b divided by 200 squared minus b divided by 300 squared minus of, okay, so 1 minus 2, so minus a minus, here also minus a, so minus minus, yes, it becomes plus, okay, is equal to 8 minus 0. Then the equation becomes b divided by 200 squared, so it becomes 40,000 minus b divided by 300 squared, it becomes 90,000 minus a, and minus minus of minus a becomes plus a, so it gets cancelled, so is equal to 8. Therefore we can get the value of b. Okay, so by taking the LCM, so next page I will continue. So if I'm going to take some LCM, so by common 9 into 4, okay, so 36. So if I'm going to take here, it is 9b minus, it is 4b minus, that is equal to 8. Therefore 5b divided by 5b is equal to 8 into 3640. Therefore b becomes, so 5,76,000 is the value of b. So the constant b is 5,76,000. Substitute b is equal to 5,76,000 in equation 1. Therefore we can get the value of a. So equation 1 is b divided by 200. So b divided by 200 squared minus a is equal to 8. So this is equation. Therefore a becomes, okay. So this side is 14.4 minus a is equal to 8. So a is equal to 14.4 minus 8, which implies a is equal to 6.4. Excuse me. So substitute a is equal to, so substitute a is equal to 6.4, comma b is equal to 5,76,000. So that we can get the value of px and sigma x. Okay. So therefore sigma x formula, that is hoop stress, maximum and minimum stress. So maximum and minimum stress. Here sigma x formula is equal to b by x square plus a. Okay, so if x is equal to r1, then sigma x is equal to, that is sigma r1 is equal to r r1 value is 200. So sigma 200 is equal to b 5,76,000 divided by x square 200 square plus 6.4. So 14.4 plus 6.4 becomes 20.8 Newton per mm square. So sigma R1 is equal to sigma 200, okay, is equal to 20.8 Newton per mm square. Next, if x is equal to R2, that is 300 mm, then 300 is equal to 576,000 divided by 300 square plus 6.4. So 576,000 divided by 40,000. So divided by 90,000. So 12.8 Newton per mm square. So this is the value of sigma R2 or sigma R 300 mm. So this is the maximum and the minimum hoop stress values. So now they have mentioned, okay, draw the stress radial pressure distribution and hoop stress distribution across the section. So the diagram we have to draw. This is the center point O, and this is the value of R1 is equal to 200 mm. So here this is our cylinder, okay, and this is the outer surface of our cylinder. So R2 is equal to 300 mm. Okay, so here our pressure distribution diagram. Okay, so internally we can have two pressure. Okay, one is fluid pressure, then another one is our hoop stress. Since we all know that, so at inside Px is equal to P naught, that is equal to 8 Newton per mm square. So this is the value of 38 Newton per mm square. And inner side we can have sigma 200 or sigma r, which is nothing but 20.8 Newton per mm square. Okay, on the outer side we can have only external pressure. Okay, so the external pressure, there is sigma 300 is equal to 12.8. Since we know that at outer surface, if x is equal to r2, px is equal to 0. So 0 is here. Okay, and sigma 300 is equal to 12.8 Newton per mm square. So it should be like this. Okay, so the diagram. So this is our diagram. Okay. So internally we can have two things. One is P naught plus sigma R1. Okay. Then outer side we can have Px value is equal to 0. Okay. So that we can have only sigma R2. So this is our internal, that is internal pressure, stress distribution. This is internal stress and this is outer stress. So this is our stress diagram. So did you got it, Ran? Thank you all.